Good afternoon, everyone. This is Anurag Pande, your instructor for CE 321, Fundamentals of Transportation Engineering. And here today, I'm going to talk about sort of our last set of content that relates with operational evaluation of transportation infrastructure. It'll primarily focus on uninterrupted flow for vehicles, and then also, touch upon a little bit about interrupted flow when that happens on certain streets. So this is sort of chapter 2 and chapter 3 of your text. I'm going to get started with chapter 2 today of your textbook. And here is, I want to just quickly share my screen. So this is sort of the, your week 5 content for the summer session. You have the slides here for the traffic flow measures. I'm going to record this lecture I'm recording. I'm going to post this video as well on your Canvas page. But in addition to this lecture, I have 3 additional lecture videos from Dr. Robert Bertini, who is now the Department Chair of Civil Engineering at Oregon State University. He used to be a former colleague of ours, and he and I did a lot of work together on sort of developing this class, content for this Fundamentals of Transportation Engineering class. And I'm going to rely on 3 of the lectures from him. They're short lectures. One of them is 25 minutes, 6 minutes, and about 10 minutes or so. And these lectures are going to go a little bit more in-depth concepts of the basic traffic flow measures. And then once we have learned about those measures in this chapter 2, and through these videos by Dr. Bertini, what we'll do is we'll move on to use those measures. Then we'll move on to see how we use those measures and apply those measures to basically assess the performance of a freeway, for example, or assess the performance of what happens in a traffic queue and things like that. So we'll basically try to apply these concepts in the next set of lecture for chapter 3. So let's go to the lecture right now. I'm going to go ahead and move it to slideshow. And again, this is chapter 2, and just like before, I will point out as for some of the sections, I'll point out where you can get further information from your textbook. And so before we get started on the actual measures of traffic flow, I think it's important to understand that the way we plan out the roadway infrastructure is that we think about what is the purpose of that infrastructure, right? So there is, for example, if you think about the roadway infrastructure in San Luis Obispo, you have US 101, which is sort of the freeway. And then you have major arterial streets like Broad Street, for example, or Higuera Street. And those are sort of your major arterials, or Los Osos Valley Road through the southern part of town. And Grand Avenue, you can think of that as a major arterial as well. Monterey Street is a somewhat major arterial. And then you have sort of these minor streets that you may not remember the name of because, unless you're talking about streets in your neighborhood. So what you can see is that there is, this is sort of a fictional map of a fictional location where you have sort of the freeways, and freeways have sort of these axis separation. So you have these interchanges that are denoted by these circles here, okay? So basically what the interchanges are trying to do is trying to separate out the traffic from meeting each other so that they don't meet at the same level. So that when you have to go from one roadway to the other, so for example, if you have to go from this freeway to this major arterial, you are able to use the ramp and without having to interact with the traffic that's already on the major arterial. Obviously, that does not happen on an intersection like this, right? For example, when you have a traffic light or a traffic signal, you're going to have a common area between the 2 streets, and that leads to slowdown, that leads to conflicts. So then if you want to keep the traffic moving, we'll sometimes provide the interchanges. And again, we have to be very careful about where we provide these interchanges because there is a concept called induced demand, and which you'll learn about more in CE 528, which is the transportation economics and analysis, and also probably in CE 523, which is about travel demand modeling. And induced demand is the idea is that if we build the infrastructure, more people would want to use the infrastructure using their cars. So these interchanges between freeways and arterials and these sort of limited access facilities, they're designed to move the cars very fast And sometimes when we create this type of infrastructure in the middle of the city, that leads to more traffic, more congestion, because through this infrastructure, more people want to use those types of roadways. But the major point I'm trying to make here is that all these different pieces of infrastructure have, for the purposes of this class, all these major sort of types of roadways have different functions or different purposes. So when you have the neighborhood distributor, or the local web access only function, like the street that goes right to your house, that will have sort of access only function. So we'll try to minimize the speed on those on those roads. We're going to make sure that people can access the roads right from their driveways, and people are slow in moving through those streets. So we'll probably have even some traffic calming infrastructure there. But on the other hand, as you sort of move in a different direction in that hierarchy, as you move in that hierarchy, then you have these major arterials that will still try to prioritize speed, although that may or may not be a good idea if for a town like Slough, where we are still a relatively small town, and we can get from one point to the other, maybe potentially using a bicycle, or if you want to navigate the grade more easily through e-bikes. So then maybe the function is now to be able to maybe increase the speed a little bit, but now sort of prioritize the movement a little bit more, prioritize the mobility a little bit more. But then on the other spectrum of this hierarchy, on the side of this spectrum is the freeway, the US 101, for example, where you have only ramp-only access for the most part through town. And there you're sort of trying to prioritize speeds so that vehicles that are going through can move fast through the city. And so, for example, if somebody's going from Santa Maria to Paso Robles, they should be able to pass through Slough rather quickly, and that's why we have sort of freeway types facilities. So the function of a freeway is basically just mobility, and then these local roads have only access related function. So those are the two concepts that sort of you want to get out of that figure that I just showed you. It's the access and mobility. It's the distinct functions that roads serve. If you're trying to prioritize the through movement, you're basically trying to serve the function of mobility so that people can move fast. And then land access is the accessibility. And it's basically, anybody who wants to get on that road can get on that road. You don't have to go through an elaborate ramp or a very large ramp to get to that roadway. So you're trying to maximize accessibility at that point, and that's the purpose of neighborhood streets. And then the major and minor arterials sort of fall in the middle. And what basically what it does is it allows the aggregation of traffic to achieve economies of scale in construction and operation. So if you are building the freeway, it can take all the traffic and then move them very fast. It reduces the number of conflicts. So if you have a lot of slow moving and fast moving vehicles at the same place, that leads to more conflicts, more collisions, and that's not good for safety. So it's a good idea to separate out high-speed traffic from low-speed traffic, and then helps maintain the desired quiet character of residential neighborhoods by keeping traffic away from homes. And this is something when, I don't know if you're familiar with the app called Waze, W-A-Z-E. And initially when Waze came around, even before Google Maps ultimately ended up buying the app. But when that app first came around, like around 2012, early 2010s, or maybe right before that, they were sort of trying to minimize the travel time, and they were sending a lot of traffic onto those neighborhood streets. And those neighborhood streets basically were getting a lot of traffic and pollution, and people were pretty agitated. Neighbors were pretty agitated about it. And that's basically a problem, right? You don't want to send a lot of traffic to places that are not designed to handle so much traffic. And then if you're cut through traffic, you tend to drive faster, and that's not ideal as well. So having these access and mobility functions separated helps us in a lot of ways in sort of keeping the right kind of traffic at the right kind of places. So this is sort of, we always have to keep in mind when you're trying to do any kind of performance evaluation that we're going to do in the next chapter. And then for performance evaluation, for streets that are, whose purpose is to serve mobility, we're going to have different performance measures. For streets that have primarily, an access-related measure, for those we should have different performance measures as well. We cannot use the same type of performance measure. So these performance measures that we're going to talk about in chapter 3 later on, They are based on some fundamental concepts of traffic flow. And we're going to talk about that in this chapter quite a bit. And first of those concept is time headways. Okay. Time headway is, you can read about that in section 2.1.1, and then you will also get a lot of details about these concepts of time headway in the lectures that I talked about from Professor Bertini that will be linked below in the description of this video, but then also on your Canvas page if you're enrolled in the class. Now, here we are going to primarily do examples through some numbers. So the way we measure the time headway is basically what we try to do is so let's say if this is my roadway location. So I'm drawing a roadway location, and let's assume that this is sort of the roadway location here. And it's just maybe this lane is going one way, the other lane is going the other way. So let's say if this lane is going this way, and then that lane is going that way. If you have these roadways and then you draw a line on the road that looks like this, if I draw a line here, excuse me, if I draw a line here and I stand at this point, I want to make a quick check mark here. If I draw a line on the road and stand here and start to measure the time at which vehicle number 1 crossed the line highway. So let's say start measuring, and I have a stopwatch, and every time a vehicle passes through this line, what I do is I make a point on my stopwatch and then just kind of count at which point it crossed the mark. So the first vehicle, it crosses a 6.52. I don't have any headway yet. The front bumper of the vehicle crosses the line, and I make a click on my stopwatch and I record the time that came out to be 6.52 seconds. And then the next vehicle came and passed the same point, the front bumper, and that would be 11.26. And then I can measure the difference between the second vehicle's passing and the first vehicle's passing, and that's 4.74 seconds. So the units here are pretty important, and I want to make a note of those units. So that unit will be here as seconds. Okay, so seconds is difference is the time, is 4.74 seconds. And then when third vehicle passes the line, I note that time as well. It's 14.59 seconds, and that gives me 3.33. So you could basically see that the values in the last column are difference between consecutive vehicles passing the same point on the roadway. And I can do the same measurement for the other side. I'll just need to do it for the other place. Now, if you do these measurements for a long time, for 1 hour period and so forth, you can estimate what we call an average headway. The average headway would be basically the last vehicle passing and the first vehicle passing, and then the number of headways you observed. So it's 28.3 is the fifth vehicle passing, 6.5 is the first vehicle passing, and you divide that by 4 headways because you're going to measure the 1 headway, second headway, third headway, and fourth headways. You're going to measure 4 headways. So you could get the average headway in this case by doing 28.3 minus 6.52 divided by 4. And then you could do this for many, many vehicles. Now, one question I have for you is that, is there another way of measuring the average headway? Yes, absolutely. There is another way of measuring the absolute headway, is that you can also average out these 4 numbers, and you're going to get the same 5.445 seconds of headway. So if you averaged out 4.74, 3.33, 4.74, 8.97, you will get the same number of same amount of average headway, which is 5.445 seconds. Now, headway basically defines on average what's the difference between 2 consecutive vehicles passing the same point on the highway. Now, the way we measure it is that we always want to measure it consistently. So if you're looking at the front bumper of the vehicle passing through the green line, this is how we always want to measure the headway. So we always want to look at front bumper of each car. So these time are recorded at the same time. Now, there is another related concept that's called gap. And the way we measure gap is the gap between consecutive vehicle will be the rear bumper of the front vehicle and the front bumper of the, the rear bumper of the front vehicle and front bumper of the rear vehicle. So that would be is considered the gap. So headways and gap are a related concept, but they're measured slightly differently. Gap is basically when the back of the front vehicle passes that time subtracted from when the front of the next vehicle passes. When we are measuring headways instead, it's always measured from front bumper of each vehicle. So it's front bumper of vehicle 1, front bumper of vehicle 2, and so forth. And that gives us headways. And gap is a slightly different concept, even though both are obviously related. Now, if you can estimate the average headway, and this average headway is sort of maintained consistently, you're in a sort of a steady state situation, you can convert average headways. You can convert average headway into what we call the flow rate. Okay, so sometimes you'll hear the term flow. Sometimes you'll also see the term observed to be flow rate. Okay, and the idea of flow rate is it's always measured per hour basis. Okay, so traffic volumes are traffic counts made over some specific period of time. So this could be traffic volumes, could be hourly volumes, but they could also be daily volumes. They could be weekly volumes. So we are interested in the daily volume. Sometimes we are interested in the 15-minute volume, and you'll see that in just a few minutes here. But then we are also, when we talk about volumes, they could be over any time period. They could be daily volumes. They could be weekly volumes. They could be annual traffic. They could be 15-minute traffic volumes as well. But anytime we start to talk about flow rate, this is the most important thing, is that anytime we talk about flow rate, they're always measured on a per hour basis. Okay, so we always want to measure it on per hour basis. So the equivalent hourly rate of vehicles past a point during any time period, the equivalent hourly rate, right? So that's what we call, so that's what defines flow rate, or simply flow. So anytime we talk about flow and flow rate, that's always measured hourly rate. Okay. Now, one thing about the headways that we just measured for in the previous graph, you can always convert headways into an hourly flow rate. Okay, if the consecutive gap between two consecutive vehicles is 5.445 seconds, okay, how many vehicles are you're gonna observe in terms of average headway into flow rate? That's pretty easy to do, because each hour has 3,600 seconds. Because each hour has 3,600 seconds. So at one vehicle every 5.445 seconds means you can always divided by the average headway. 3,600 divided by average headway will always give you what we call flow rate. So if you want to convert headways into flow rate, this is the way to do it, is that you do 3,600 divided by the average headway. So in this case, in the previous example that I just showed you, divided by 5.445, and that gives me a flow rate. And typically, flow rate is what defines capacity of a roadway segment, just to kind of give you an idea. And sometimes, you could once you have the per hour basis, you can convert that into per hour per lane basis as well. So sometimes we'll define capacity of a freeway is to be like a highway, capacity of a highway to be something like 2,200 cars per hour per lane. So each lane of the freeway can take in or can pass through 2,200 vehicles per hour without sort of having any sort of huge congestion. There might some slowdown somewhere along the way, but 2,200, even some cases when your speeds are higher to begin with, you can go as high as 2,400 cars per hour per lane. So each lane of the freeway can handle about 2,400 vehicles per hour. So that sort of gives you an idea about, and so maximum flow rate that can pass through a point is how we define capacity. So flow rate is a very important concept here. So because we have a section on flow rate, we also need to think about the peak hour factor. And peak hour factor comes from the fact that, traffic flow is not uniform, right? Even within 1 hour of traffic, the traffic flow varies between, every minute, like, different number of cars would come through an intersection or a roadway segment location. So if you sort of, we gave you an example at the very beginning of standing on the side of the road and draw a line, you will see that the headways vary considerably. So some periods you have a lot of cars coming in, and some other periods you don't have as many cars coming in. So traffic flow is never uniform, never fully uniform, and it does vary quite a bit. Now, even during the most busy hour of the day, if you start to measure the traffic every 5 minutes or every 15 minutes, you will start to see a lot of variation in traffic that happens. And typically we define that variation, or how uniform is the flow. We define that using what we call the peak hour factor. Okay, what is a peak hour factor? The peak hour factor is used in design to adjust the design hour volume predictions to peak 15-minute predictions. So because we know every 15-minute, and then, this flow can measure every 5 minutes as well. So you could define a peak hour factor for 5 minutes as well, but it's just that the typical practice that we use in traffic engineering, it's every 15 minutes. So instead of so we look at the peak hour, and then within the peak hour, we look at how much traffic came in every 15-minute period. Okay. And that's what we use to then convert the peak 15-minute arrival rate or a peak 15-minute traffic volume, and we multiply that by 4 to make it an equivalent hourly flow rate for capacity analysis. And that's what we use. And that's why we want to point out so you might be wondering, okay, so we want to basically, what we are saying, Professor, is that we want to account for the worst 15-minute during the peak hour. So how does it measure uniformity? Okay, how does the factor measure uniformity? Yes, we want to account for the worst 15-minute where most cars come in, and that all makes sense. But you at the beginning said it's measure of flow uniformity. How does that work? So how that works is like this. So for example, if you think about it, let's say you measure the volume per minute at a location, and this is what the chart looked like. That 5 vehicles coming in every minute, 5 minutes, 5 vehicles coming in every minute for 30 minutes. And then between 30 and 45 minutes now, the volume jumped up, and now you have 10 vehicles coming in for that 15-minute period. And then at t equal to 45 minutes, the volume went back down to 5 vehicles per minute. So it's volume per minute, and then minutes on the x-axis, volume per minute on the y-axis. So we define peak hour factor as total hourly volume, the traffic that came in during the whole hour, divided by the peak 15-minute flow rate. Okay, so this is pretty important here to kind of think about this, is that I'm mentioning flow rate here. Okay, so this is pretty important to note the term flow rate, because I told you flow rate is always measured per hour. So anytime we have any traffic volume, we want to measure it on the basis of per hour volume. Or we want to measure. So if you look at this chart, this 15-minute period between 30 minutes and 45 minutes is between this 30 minutes and 45 minutes is what came in. It had the highest volume, and it had a volume of 150 vehicles that came in during the 15-minute period. So we think about, okay, the total number of cars that came in is like 5 vehicles per minute for 30 minutes. That's 150 vehicles, right? So if you look at this 150, where did that came from? That for 15 minutes or for 30 minutes, 5 vehicles per minute came in. So in 30 minutes, 150 vehicles came in. For the next 15 minutes, 10 vehicles per minute came in. So another 150 came in on only 30 minutes. And then last 15 minutes, you had 5 vehicles per minute coming in. So your volume was only 75 vehicles. So the total volume that came in the whole hour is 150 plus 150 plus 75. 150 plus 150 plus 75. So that's your 375 vehicles per hour. That's what came in during the full hour. So that's your hourly volume. but you want to divide that by peak 15-minute flow rate, okay? And again, flow rate is measured per hour. So what does that denominator stand for? This peak 15-minute flow rate. This peak 15-minute flow rate stands for if this is the flow continued, if this, what happened during the peak 15-minute continued for the full hour, how many vehicles would you have come in if that continued for the whole hour? So in this case, it's 150 times 4, because if that, what happened during those 15 minutes continued for the full hour, you would have 600 vehicles come in. So basically you take the peak 15-minute flow rate or peak 15-minute volume and you multiply that by 4. So this 600 is nothing but 600 is basically equal to 150, the peak 15-minute volume, times 4, okay, is equal to peak 15-minute rate of flow. Because remember, when I say rate of flow, you multiply, you convert that into an hour. So you take the peak 15-minute volume, you multiply that by 4, because there are 4 15-minute intervals in an hour, and you get 600. Now, going back to this question that I asked you at the beginning, why is this a measure of uniformity? Now think about that. So if this volume always continued at this level, if this volume never jumped up, if this volume never jumped up and you always had this 150 sort of continue, and on this 15-minute period also only 75 vehicles came in, and then this V was also equal to 75, what would your peak hour factor look like in that case? If this was the volume at 75, you'll have 375 vehicle coming in, right? For the whole hour, you'll have, I'm sorry, you won't have 375 vehicles come in. You'll have 150 plus 75 plus 75. You'll have 300 vehicles come in total, right? And because there is no real peak in there, you can take any 15-minute period. So your peak hour factor in that scenario would have been PHF in a fully uniform demand scenario would have been 300 would have been your hourly volume. You divide that by 4 times peak 15-minute volume, that would have been also just 75, right? So you take any 15 minutes, 4 times 75, and your peak hour factor would have been 1. Okay, so that's why it's a measure of uniformity. So if you have a perfectly uniform flow, your peak hour factor would be 1.0. But if you have unevenness in the flow rates, then you will have a pretty low peak hour factor. So typically the urban areas will have a peak hour factor of 0.9, 0.92, 0.85 even, things like that. Rural area would have a little bit lower peak hour factor because rural areas have a little bit more uneven demand typically. So rural areas will have a peak hour factor of 0.78, 0.75, 0.8, things like that. So urban areas will typically have higher peak hour factor because the traffic flow is more uniform in nature. Okay. So I just want to say urban areas have more uniform flow, hence higher PHF, higher peak hour factor. Rural areas have less uniform flow. There's more fluctuation in demand, and that's why you have a lower peak hour factor in rural areas. So just wanted to make a note of that. So that's sort of some discussion of one of the traffic flows. So when we try to estimate the performance, we are interested in typically the flow rate and the speed and how congested the traffic is. And we are looking at density in that case. So we talked a little bit about flow rate and traffic and cars and counting of cars. And then now we talk about at what speed those vehicles are moving. And this is something that's called time mean speed and space mean speed. Time mean speed is a measure that we measure over, over a certain point of the road. So you stand on the point of the road and you count, you look at the speed of individual cars that are passing and you average those speeds, and that gives you time mean speed. Now in space mean speed, it's a related concept, but slightly different. You don't measure space mean speed by standing still on a point of the road and measuring individual vehicle speed. You actually look at a segment of the road and you look at sort of what speed individual vehicles are moving on that segment. Not on that point, not a particular point on the road, but over a 1 mile segment, 2 mile segment, whatever segment you're looking at. And then you measure at what those speeds are. So these are related concepts, but slightly different. I will strongly recommend that I'm going to give you the formula for time mean speed and space mean speed. Time mean speed is that, if you're standing on the road and you look at, the distance divided by travel time. So if you are basically looking at this formula right here, so let's say if I'm drawing a segment of the road, and let's say, so if you have a segment of the road, so I have this segment, and let's say all cars, it's a road segment where all vehicles are moving in the same direction. So all vehicles are moving in this direction, okay? So all traffic is going in this direction. And this is, let's say, a 1 mile segment. And this is a 1 mile segment of the road. On whatever distance, right? So let's say the distance is D units so this segment is D units. And then you have vehicles on all sorts of vehicles on this road, right? So you can have vehicles everywhere on this segment, on this D. Basically, what you do is you measure each of these vehicles, how much time did they take to traverse this segment. So you measure this time. So you have this vehicle traverse the whole segment, have this vehicle as it traversed the whole segment. You measure the time and you do distance divided by individual time. So TI is going to be the travel time for each of these vehicles in traversing this D over TI, is the segment of D miles or D units. And then D over TI will give you individual speed, and you average those individual speeds. So in this case, N will be 1, 2, 3, 4, 5, 6, 7, 8 vehicles. You take a look at what time each of these individual vehicles took, and then you average that individual speed, and you get the time mean speed. You get the average. So in this case, N will be equal to 8, 1, 2, 3, 4, 5, 6, 7, 8. So in this example that I'm showing you, N is equal to 8. And then you look at the travel time, get the travel time, TI, for each vehicle to travel distance D, okay? And that's how you get your time mean speed, okay? The space mean speed is slightly different. The way you do it is that you take the time and you average the travel time, okay? You average the travel time, okay, first. You don't calculate the speed first. You calculate the travel time first. So you get, to get the space mean speed, you average the travel time for all vehicles and then divide distance by the average travel time for all. Now, the key here is to understand that these will give you slightly different. And if you are sort of familiar with the averages, this represents sort of the arithmetic mean of the speeds. This represents what we call the harmonic mean of the speed. And you can look up those concepts. And harmonic mean, as it turns out, is always lower than the arithmetic mean. Okay, so space mean speed will always typically be lower than the time mean speed. Okay, I strongly recommend that you watch the video that is posted for specifically on this topic on your Canvas, and I'm going to link that on the description of this video as well. I'll strongly recommend that you watch these videos to clarify this concept of time mean speed and space mean speed in your head. But the big idea there is that in time mean speed, you get the speed first. Using travel time, you get the individual speed of vehicles, and then you average it out. But on space mean speed, you get the average travel time for all vehicles first, and then you divide distance with that average travel time to get the space mean speed. And the other thing is that space mean speed is always lower than the time mean speed. So when we are doing a lot of these traffic performance calculations or estimations in freeway level of service, as we're going to do in next chapter, for example, we always use space mean speed. So space mean speed is a more meaningful concept because that's the one that leads to its relationship with the flow rate and the density the concept that we're going to just talk about. Again, strongly recommend watching the video in the comments, in the description of this video, but then also on your Canvas page that specifically deals with this concept, the short video by Dr. Bertini. You must watch that to clarify these concepts. Okay. The last concept that I want to deal with here is the idea of density and lane occupancy. Okay? Density and lane occupancy. So density is also a space measure. So we've talked about some measures that you can get from the side of the road. You stand on the side of the road and have the vehicle pass by. So for example, time mean speed is such a measure. Flow rate is such a measure, is that you stand on the side of the road on a point and you look at vehicles passing that point and use that data to get some measures. And those are sort of your point measures. But space mean speed, and also just like space mean speed, density is also a measure of what we call a space measure. So you can't get it from a point on the road. But density is something that we can measure, number of vehicles occupying a given segment of the highway. So for example, let's draw out this segment of the road here. So I'm going to go ahead and draw this segment of the road. So this is, let's say this is your road, and let's assume that this low road has 2 lanes. This road has 2 lanes, maybe perhaps in the same direction. And let's say this segment is, the length of this segment is, let's just say 2 miles, okay? So I'm going to say the length of this segment, just for the sake of argument, it's 2 miles. And then if the length of the segment is 2 miles, and I want to say, okay, I want to post some vehicles on this road. So these, let's say these stars represents vehicles on the road. Center of gravity for different vehicles on the road here. I'm sorry. This is just the location of different vehicles on the road, and I have placed them somewhat unevenly, but that's okay. Maybe some of these vehicles are in process of lane changing and whatnot, but let's say these are the vehicles I've got going on the road. So to get the density, what I need to do is sort of look at that 2 mile segment of the road and count how many cars I have. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 vehicles over a 2 mile segment of the road. So obviously my density is, in this scenario, is 20 vehicles divided by 2 miles. So my density in this case would be 20 vehicles divided by 2 means 10 vehicles per mile. Okay, so that sort of is the measure of density that I'm going to use. And then density could be hard to measure because, again, you're talking about having to look at a large segment of the road, possibly through an aerial photograph, and then kind of measuring density. But we do have a better measure, or better way of measuring density is through loop detectors. And loop detectors are basically sensors that are, they used to be buried under there used to be magnetic sensor buried under the highway, but now we have different types of infrared sensors, so less intrusive sensor, like more reliable sensors. But the idea of all of those sensors is basically you can then those sensors are basically just loop detectors, and they look something like this. On a highway segment, they would be something like that. They look like, so they will be sort of drawn here. So I'm drawing these segments, and they're placed about every half a mile or so. So in a 2 mile segment, so probably have like sort of 4 of those sensors. Okay, so you'll have about 4 of these sensors, and then you might have those on every lane. You might have those on every lane here. And those sensors are pretty small, like, maybe 6 feet by 6 feet sensors. Okay, and as the vehicle sort of passes through those sensors, the magnetic field gets disturbed, and they record that, yeah, a vehicle is passing through. So they are basically a way of automated data collection on our freeways. You can actually look at the time a detector is occupied and convert that time into what we call the density. So in this case, occupancy, the concept of occupancy is called, so what we are measuring is not the vehicle occupancy. Okay, so how many vehicles, how many occupants are inside a vehicle? That's not the concept we're talking about here. Although that can be an important concept, because if you want to have some carpooling and stuff like that, we want to have more people occupying a certain vehicles. Sometimes we give high occupancy vehicles some advantages in terms of they can go into certain lanes without any tolls and things like that. So we have those HOV things. But when I say occupancy in this context of this lecture and this class, I'm not talking about vehicle occupancy. What I'm talking about here is lane occupancy. And these detectors can help me measure lane occupancy by looking at the proportion of the time a loop detector is occupied or its magnetic field is disturbed because a metallic car or metallic truck is passing over that loop detector. And this is a proportion of time, so it's measured as a fraction. So O is the occupancy. O is measured as a fraction. And if I want to sort of look at the time a loop detector is occupied, I can convert that lane occupancy into a density using this formula, where a density could be obtained, the density D can be obtained by 5280 times O. And this 5280 is nothing but a feet to mile conversion, because I'm going to measure my LV, which is the length of the vehicle, and LD, which is the effective length of the detector. And that's why I'm underlying it, is because it's effective length. So here, O is D is density. So that's what I'm trying to derive, because it's hard to measure directly. So I'm relying on loop detectors to measure my density. So my D is density. My O is occupancy, or I should probably be careful here and say lane occupancy. And it's measured as a proportion of time. So it's just a fraction. So 0.1, 0.2. LV is vehicle length on average in feet. So if you are mostly made up of passenger cars, your vehicle length would be 20 feet. But if you have a higher proportion of truck, maybe it can go up a little bit by like maybe a few feet. And that you'll have to rely on, like, what kind of vehicles you have, what kind of vehicle fleet you have passing through. But LD is the effective length of the detector. And what do I mean by effective length? It's basically the magnetic field of these detectors is disturbed even if the vehicle, is getting close to them. So the metal starts to interact with the magnetic field of these detectors a little bit sooner. So you basically have to add like maybe a couple of feet to the length of these detectors. So if these are 6 feet detectors, the effective length might be something like 7 or 8 feet. And anytime I'm going to give you a problem, I'm going to give you the effective length in feet. It's measured in feet. And then this 5280 is just a feet to mile conversion factor. So you can derive your density in vehicles per mile. So your unit of your density will still be vehicle per mile because of that 5280 factor that I multiplied by here. And you could use that to derive density. Now, density is a very important measure of congestion. Okay, that's pretty important for us. And now that you've learned about the space mean speed, density, and flow rate, now we can start to think about how we can start to relate those 3 measures to get the vehicle performance measures. How those things might be related. Okay, so think about this for a second. So let's say you have a certain segment of the road. So let's say you have a certain segment of the road. I'm going to draw that again here. Oops. Let me draw a line here. So let's say if I have a certain segment of the road, and let's just say this is only going in one direction. I'm interested in just going one direction for now. And then I'm standing here on this side of the road. I'm standing here on the side of the road, and I'm counting cars that pass by this point right here. And this is the place I'm standing and counting cars, okay? Now, as cars pass by, okay, let's say these vehicles on a space mean speed basis, on average, space mean speed is 60 miles an hour. Let's say that on average, the cars are moving at 60 miles an hour, a space mean speed. So if I look at a segment of car that's 1 mile behind it, and let's say on each of these segment of the highway, if I look at sort of, and this flow is in steady state, and I look at each mile segment of the highway, I have 20 vehicles per mile is my density. Okay. My question to you is, can you think about if the cars are moving at 60 miles an hour and the density is 20 vehicles per mile, and each mile has 20 vehicles, and I stand here, and then that's the kind of flow that is basically existing on this segment of the road for miles and miles and miles. And let's assume the steady state for a second. My question to you is, how many cars am I going to count in 1 hour period? Okay, how many cars am I going to count standing on this point where if I look at the upside, the traffic is moving this way, the traffic is moving this way, and I'm counting car here, and then this is the steady state as far back as you can go of traffic. The traffic is moving at 60 miles an hour, and my density is 20 vehicles per mile. Okay. So that means if I stand here for 1 hour, okay, I stand here for 1 hour, I will, and the cars are moving at 60 miles an hour on average, right? If I stand here for 1 hour, the cars that are right now 60 miles away would have arrived this point in 1 hour period. Okay, all the cars that are about 60 miles away behind me, 60 miles upstream of this point, would have arrived in 1 hour at this location, right? Now, only I need to figure out is that if I want to figure out how many cars am I going to count in 1 hour, I need to figure out how many cars are there in that 60-mile segment. I know that my density is 20 vehicles per mile. So that means there are 60 times 20 cars lined up, or at least moving towards me. And those are the ones that would arrive here within next 1 hour. So if I count here for 1 hour, I would get 60 times 20 cars. I will count 1,200 vehicles per hour. So that gives me some relationship between the space mean speed and my density and my flow rate. And sometimes, you might see different nomenclature for these. So if you look at this one right here, so if you look at Q, S, and D that I'm depicting as flow, speed, and density, sometimes you might see different values or different notations for these. So sometimes speed might be represented with a V or a U. Okay, sometimes people will represent V or a U as for your speeds. That's possible. Density is sometimes measured as K. Sometimes people will sort of measure density as K. Okay, so remember that depending upon the textbook that you refer to, there might be different terminology, but the idea is that if you're talking about the kind of flow that happens on a freeway, we call it uninterrupted flow. Okay, uninterrupted flow where you don't have any traffic signals, interruptions, you don't have any stop signs on the main line of the roadway. On like a facility like a freeway, like a US 101 through San Luis Obispo, for example, you can always approximate the relationship between flow, speed, and density. You can always define that relationship as Q, the flow rate equal to speed times density. And this is what we call fundamental relationship of uninterrupted flow. Okay? So this is the fundamental relationship of uninterrupted flow. Q is equal to S times D. Okay. Now we can define these, and there could be relationship between speed and density. There could be relationship between speed and flow. There could be relationship between flow and density as well. But this is sort of the fundamental relationship that would always be valid. Flow equal to speed times density. Now, are speed and density also related? Okay. They might be related, right? So think about that. If you're on a congested set of roadway, if you have high density on the roadway, more vehicles per mile, what happens to your speed? Okay, speed does go down, right? Speed does go down. And there are different ways of depicting that relationship. Speed, as your density goes up, as your density increases, as your density increases, goes up, go from left to right on the x-axis, your speed should come down. So you could depict that relationship with a linear line with a negative slope, right? So you could depict that with a negative slope. So if b is a positive number and I put a negative sign here, so it's a minus bd, okay? So you could depict it that way. There are other ways of depicting that. There are other ways, like maybe these things are not exactly fully linear in nature, but as long as you're depicting it as density increases, speed comes down. There could be many different ways. For the purposes of this class, I'm only going to focus on this linear negative slope relationship between speed and density, and this is what we call the general form is called, this linear general form is called Green-Shields model. There are other models like Greenberg's model that assumes a logarithmic asymptotic relationship and things like that. And you will learn about that if you're interested in taking that class, CE 529, Modeling and Simulation. We'll look a little bit more in depth on where those relationships, why does it, theoretically, what does that relationship look like and how we can derive it. So the Green-Shields model and the Greenberg's model, and we got into a lot of different sort of theoretical traffic flow theory stuff in that class. But for now, for this class, we'll just focus on the Green-Shields model, which defines a linear relationship with a negative slope between speed and density. You can then derive these parameters of this relationship. So speed and density being the variables. So this S and D are the variables of this relationship. So this S and this D right here, they are sort of the variables of the relationship. And A and B are parameters of this relationship. So, okay, there is a difference between variables. Variables are what goes into your graphs as axis. Okay. The parameters would be what defines this relationship. So the slope of this line would be a parameter. The intercept of this line would be a parameter as well. So think about this. So S and D are variables. So speed and density are variables here. A and B are parameters. So what are those parameters, really? You can derive those parameters by thinking about what they represent, what this relationship represents. So I want you to focus on this point right here. I want you to focus on this point right here. What is happening at this point? What's happening at this point? So I'm going to draw a next mark here. What's happening at this point? And I also want you to focus on what's happening at these the other point on the x-axis. So let's first think about point number one. What's happening right here? At this point, what is the value of density? The value of D, because it's the y-axis or the speed axis. The density here is 0. So that means you have, so if you look at this characteristics of this point, D is equal to 0. So density is 0. That means there is no traffic on the road. And we know what happens when there is no traffic on the road, right? People would go as fast as they want to go, given the design, maybe the fear of getting a ticket or whatever. So when the density is 0, the first driver, the only drivers that are going to be there, they're going to be driving as fast as they can, given the design. And the speed here is called FFS, or free flow speed. So we call the speed here to be the free flow speed. Okay. Now let's think about this point, the other side of this, right here. Now this is on the density axis. That means the speed here is 0. So here, what happens here is that S is 0. So speed is 0. And what is the density? So density here is so high. Density here is so high that nobody can move anymore. It's so congested right now that nobody can move theoretically, and speeds have completely come to a complete stop. And that density is the highest density, or what we call the jam density. Speed is 0 at this point, and the density is called the jam density. So we can use this information, then derive the values of these parameters. So we can derive the slope based on these points. We can derive the intercept of this line based on these points. So we can derive the A and B. Now, the other thing about this is that once we know the parameters of this relationship, we can then solve some problems. We can then solve some problems that are asking us to derive. So if you know the speed and density relationship, and you know that this is the fundamental relationship as well. So if Q equal to S and D still applies, and then you have derived this relationship as well, the Green-Shields model, and you've derived the parameters of that using the free flow speed and the jam density, you can use that information then to relate flow with density, the flow rate with density, or you can relate speed with the flow rate. So you can derive speed relationship and flow rate relationship as well. And then this is what those relationships might look like. So if speed versus flow relationship would look like a parabolic relation, and where the flow rate is maximum, that's what we call the capacity relationship. And this is the type of chart. This is the type of chart that we use in chapter 3 to derive the free will level of service. So this is what is called the speed versus flow relationship. If you go back and look at the next chart here, you could derive so you have flow on the x-axis, so speed on the y-axis. You can also derive flow and density relationship. That will also be parabolic in nature. And you have the capacity as the maximum flow rate, and the density. And again, at jam density, the flow will be 0. What we'll do in the next video, and I'm going to link that video also with this, is work on this example problem where your speed relationship is given, and I'm asking you to derive all these parameters. I'm going to stop here. Thank you so much for your attention. We'll solve this example problem in another video.